In pharmaceutical water systems, total organic carbon, or TOC, acts as a microscopic shield. Organic carbon molecules enclose and protect bacteria from standard sanitization methods. Once protected, those bacteria multiply rapidly and release endotoxins, causing severe drug degradation before the product ever leaves the vial. Welcome back to the Indian Pharmacist, where we break down the exact engineering and compliance protocols you need to navigate strict regulatory environments. Today, we are going to build a statistical process control chart from scratch. We will set strict mathematical control limits for your facility's water system, and we will audit the physical piping geometry that dictates your water purity. To follow along and apply this to your own facility, gather your last 90 days of water system TOC data and pull your facility's piping schematics. High endotoxin levels caused by unmanaged organics trigger immediate stop-ship orders for injectable drugs. Mastering this specific tracking protocol ensures you catch contamination early and pass your FDA audits without disruption. The United States Pharmacopeia sets the baseline law. Under General Chapter 643, the absolute legal limit for TOC in purified water is 500 parts per billion. To put that scale into perspective, 500 parts per billion is equivalent to dissolving half a teaspoon of sugar into an Olympic-sized swimming pool. Many engineers treat that 500 parts per billion ceiling as the only metric of success. They wait for the water to approach that line before taking action. But any rising organic trend, even well below that 500 limit, means contamination is actively building inside your pipes, shielding pathogens and allowing biofilms to take root. You cannot manage what you only measure at the ceiling. True compliance requires tracking the daily data to establish your specific system's normal behavior. This graph maps exactly how we find that normal baseline. By inputting your 30 to 90 days of historical data, we establish the standard hum of your facility. For this example, the data hovers consistently around 15 parts per billion. From this specific dataset, we calculate two numbers: the mean, which is your system's average, and the standard deviation, represented by the Greek letter sigma, which measures the typical variance in your data. We use those calculations to set our first guardrail, the alert limit. This is calculated as your mean plus 2 standard deviations. Think of this line as the smoke. When your data intersects this alert limit, it is an internal warning. You do not need to file formal paperwork yet, but your maintenance team must be dispatched immediately to inspect the system's filters. Next, we set the action limit. This is the mean plus 3 standard deviations. This line represents the fire. Notice how far above this limit the actual USP 500 parts per billion ceiling sits. If your data breaks through this 3 sigma action limit, normal assumptions halt. You are now required to initiate a formal root cause analysis. By setting these mathematical guardrails, you convert TOC monitoring from a passive pass-fail check into a proactive early warning system that catches variations long before they breach regulatory limits. When the data spikes, the answer usually lies in the facility's physical geometry. We audit this using the ASME BPE standards. Looking at this 3D model of a piping intersection, we apply the 3D rule for dead legs. If the branch length is too long relative to its diameter, water sits still. Organics accumulate in these stagnant zones, feeding bacteria. To counter organic buildup, we rely on 185 nanometer UV oxidation. As this animation shows, high-intensity UV light creates hydroxyl radicals in the water. These radicals literally burn complex organic molecules down into carbon dioxide and water. However, these UV lamps have a strict service life of about 8,000 to 9,000 hours before their intensity drops. When an expired UV lamp loses its oxidizing power, or when a stagnant dead leg goes unnoticed, organics multiply. These invisible physical degradations are the direct cause of the special cause variation spikes we mapped on our control charts. The moment your 3 sigma action limit is breached, you begin the root cause analysis workflow. This checklist models your first phase of investigation, the external environment. You check for recent spring thaws that wash organics into the feed water, and you review local data for aging municipal water pipe breaks that introduce organic slugs. Next, you move down the checklist to internal facility factors. You verify the condition of the reverse osmosis membranes for fouling, and you log the exact operational runtime of your UV lamps. Once you complete the checks, you compile your statistical charts, your dead leg geometric measurements, and your checklist findings into a formal internal audit report, presenting a documented history of trending the data, investigating the spikes, and correcting the physical flaws prior to hitting 500 parts per billion proves your system is under control. That paper trail is your defense against receiving a 483 warning letter from an FDA auditor. You now have a complete diagnostic framework. You have calculated statistical process limits based on your own historical data, audited your physical piping geometry, and built a step-by-step root cause analysis checklist. Proactive engineering relies on 3 principles: trend your data continuously, track your system geometry rigorously, and treat the root cause immediately to maintain the purity of your drug products. If you are responsible for maintaining compliance in an FDA-regulated environment, hit the subscribe button for more deep dives into the mechanics of pharmaceutical engineering. Stay cure, and we'll see you in the next one.